All right, so today's lesson we're going to go over 10.4, which is using inscribed angles and polygons. So the first thing we need to know is what is an inscribed angle. And as we see here, an inscribed angle is an angle whose vertex is on the circle and whose sides contain chords of the circle. So it is on. That's the big thing. Your vertex is on. So we see here on our little diagram that my vertex is on the circle. Not to be confused with a central angle whose vertex is the center of the circle. An inscribed angle has a vertex on the circle. However, just like a central angle, the inscribed angle actually intercepts the circle, and that interception creates an arc, which we call the intercepted arc. So again, the intercepted arc, the arc that lies in the interior of an inscribed angle and has the endpoints on the angle. So we see here we have our endpoints here and here. And you can call it A, B, whatever you need to call it. But that is my intercepted arc. Central angles do the same thing. They intercept the arc and they create that minor arc. Inscribed angles will create, an arc as well, intercepted arc, not necessarily minor. All right. From there, how do we find the measure of it? Now, if you remember, your central angle, when you were talking about it, when it intercepted the circle, its angle was equal to whatever the arc was, or the arc was equal to the angle. However, with an inscribed angle, the measure of the inscribed angle is 1/2 the measure of the arc. So we see here that angle ADB is 1/2 the measure of the arc AB. So for example, if I told you AB was 100 degrees, then that would mean the angle ADB would be 50. All right. Or vice versa, if I told you the angle ADB was 50, then the intercepted arc was 100. So you see it can work both ways. That you either take half the arc or the arc is double the angle, and you're going to need to know how to do it both ways. All right, so here we have a couple examples. You're going to see things like this where we get our diagram. We have Q, R, T, and S with P as my center. And that's also important, guys, is that if you start recognizing that, hey, look, TR here, that is a diameter. So that's probably going to come into play usually in your problems. You need to be able to recognize those things when you have them. It says, once you find the measure of angle T. So we're looking at T, angle T, which is right there, that angle. And we don't know what the angle is. Well, we see that angle T intercepts arc RS. And since my arc RS 48, we know that T has to be 1/2 of that. So it's 1/2 of 48, which gives us 24 degrees. All right. Our second problem says the measure of QR. So we're looking for QR. We're looking for this arc out here. Well, there's not an angle that opens up to it. However, remember what I mentioned earlier, that we know that RT here is a diameter, which means it does cut the circle in half. So we know from T all the way to R here, that's 180 degrees, right? So we have 180 degrees, and we need to find what QR is, but we don't know anything about that. But we do know that QRT here, this angle right here is 50 degrees, which means that QT has to be 100. And as you guess now, we can just subtract 100 from 180 and get my answer. So 180 minus 100, and that gives us 80 degrees. So we see that QR equals 80 degrees. Now again, don't get caught up in the size or the shape or whatever of what one looks like versus another. Just, again, take the numbers as you see them. Because again, as always, drawings are not to scale when we're doing problems in math. We want to look at what we're looking at. All right, so now we get to kind of like a bow tie problem. We get the bow tie inside our circle here. And we want to find RS. So we're looking for RS here. RS, my arc there. Now we see that RS actually has two different angles that open up to it. We have STR, and we have SUR. And we know SUR is 31, which means that RS here has to be 62. So we know RS is 62 degrees. Because again, my intercepted arc is twice my inscribed angle. So you just double the angle. And then it wants us to find STR. So STR. We're looking for that angle right there. What is that angle? Well, since it intercepts the same arc as SR, which is 62, it has to be half. So we know it is 31. And what this leads us to is this next theorem. And the theorem states that if two inscribed angles intercept the same arc, then they are congruent. So as we just saw in our previous example here, we see that STR and SUR, they both intercept RS, and look, they're both 31, so pretty much exactly the same as we just saw. So in our example here, ADB is congruent to ACB because they both intercept the arc AB. Now, based on this is not the only two angles that are congruent, because we could actually prove that DAC and DBC are congruent because both of them intercept arc DC. So there's actually just multiple than one. There's more than one when you see these bow ties. There's always at least a second one. And if you really wanted to get into details and bring back previous stuff, you can prove these two triangles are similar by angle, just for kicks. All right, so here's an example. Name two pairs of congruent angles in the figure. Now, they give you A, B, C, D. That's a lot of angles in there. So I suggest look at your diagram first and figure out what are my angles that are marked. So we see that I have an angle that opens, let's say, KJL, right? That angle opens up to KL. The same as KML opens up to that. So I know KJL, KML. So I'm looking for J and M in the middle. They're congruent. And then I also know, going the other way, that JKM and JLM are congruent because they both open up to JM. So I'm going to look for those four angles when I'm looking at it. So I'm looking for K and L in the middle, so it's JKM and JLM. JKM, JLM. Well, I can see that A, JKM is not congruent to JLM. That didn't work. C, JKM, congruent to JLM. That's so far so good. And then I got to make sure it's KJL, which works, to KML. There we go. So C is the one that matches that. Kind of an SAT type question with multiple choice. Be prepared. You'll probably see that on your final. All right, then we got three more examples using different ways of looking at it. So let's look at each one separately. Find the measure of the red arc or angle. So in this case, here we go. We got angle HGF, and we see that it intercepts the arc HF. So my angle, and we remember, is 1/2 of the arc. So it's 1/2 of 90, which means it is 45 degrees. All right. And then we look at the second one. And it gives us the angle TUV. And it wants to know what is the arc TV. Well, if that's 38, we know that the arc is double the angle. So in this case, 76 degrees. And then in my last one, we see we have angle ZYW, and we're looking for angle ZXW. Well, you notice these are two angles intercepting the same arc, which is ZW, so they must be congruent. By the there, we had it just above, so we know it's just 72 degrees. Now, if you wanted to, you can go, okay, 72, double it, that's 144, then take half that, go back to 72. But the theorem helps us to kind of just skip that part. We can just go straight to, they're congruent, they're equal. All right. Now, we've seen a couple shapes before, and if you remember back to our special segments and triangles, they help create some of these little shapes. We have inscribed polygons. Now, inscribed polygon just means that there is a polygon that is inside a circle, and then all its vertices are touching the circle. So I got two examples here, inscribed triangle and an inscribed quadrilateral. Now, we're going to primarily talk about those. But guys, every shape has a possibility of being inscribed. And if you are regular, you will always be inscribed. All right. If you're not regular, not necessarily. Some yes, some no. Mostly quadrilaterals and triangles will be that, but not all the rest of them, like pentagons, hexagons, octagons, blah blah blah. Not all of them, but these will be for the most part. Circumscribed circle is a circle that contains the vertices. Basically, guys, inscribed means inside, circumscribed means around, outside. Kind of like circumference, it's around the circle. Or if you circumnavigate the globe, it means going around the earth. So, based on that, since we now know what an inscribed circle is, that we do have some theorems that play with it. So theorem 10.9 says, if a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. Also, if one side of the inscribed circle is a diameter, then the triangle is a right triangle and the opposite angle of the diameter is a right angle. So basically, the guy's saying is, given we have an inscribed triangle, if you know that the inscribed angle is 90 degrees, then you know that that side opposite that 90, in this case B here, my hypotenuse has to be the diameter. Because if you think about it, guys, if you look at the intercepted arc, if this is 90, B is 90, then what does that make AC here? It makes it 180 degrees, which makes this from A to C a semicircle, which means that AC by definition is the diameter since it cuts the circle in half. Vice versa, if you know it's a diameter, AD is the diameter, then you know that the inscribed angle that goes from A to C and touches somewhere anywhere between A and C, that B, that it's going to be a right angle in there. So it works both forward and backwards. And you see here, measure of ABC equals 90 if and only if AC is the diameter of the circle. So it's both ways, forward and backwards. You got to be able to recognize them. All right. Then our next term deals with quadrilaterals. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So not to get this confused with parallelogram, which means opposite angles are congruent. This is opposite angles are supplementary. So we see here that E and G have to add up to 180. D and F have to line up equal 180. All right, it's the only way it works. So think about it easily. Guys, all rectangles can be inscribed in a circle because their opposite angles are always supplementary. 90 and 90 is 180. Same thing with squares, but of course squares are rectangles. So we're going to get problems like this. And yes, some of these problems are going to have systems of equations. So you need to be ready to deal with them when you see them. All right, so here we go. We got Q, P, S, R, and it is inscribed inside a circle. And since we know that opposite angles have to be supplementary, we can set up our equations to solve for x and y. X plus 80 equals 180. So in this case, x equals 100. And then my second one, y plus 75 equals 180. So y equals 105. And then we can do the same thing over on the second question here on part B. We see that 4b and 2b, they have to read up 180. So you get 6b equals 180. So b in this case equals 30. And if I wanted to, I could find the measure of the angles. That'd be 120 and 60. And then we know that 2a and 2a have to add up to 180. Which is 4a equals 180, so a equals 45, which means each of these angles is a right angle. Which in all reality, guys, kind of makes this a kite. Think about it. But again, that'd be another day. All right, here's another two examples of this. So look at the first one. We have x and 82, y and 68. So x plus 82 equals 180. So x equals 98. And then y plus 68 equals 180. y equals 112. And now this next one, 6, brings in a little more algebra. We have c and 2c minus 6 and 8x and 10x. I'm going to start with the x's. 8x plus 10x equals 180. 18x equals 180. X equals 10. And then c plus 2c minus 6 equals 180. So 3c minus 6 equals 180. 3c equals 186. Remember to add 6, not subtract it. So c in this case equals 62. And again, when you start seeing some of the problems, you probably will see a system of equation in this one. All right, so that's the lesson for today. Make sure you do your homework well, and I'll see you next time.